Education. Selamat sore semuanya. Assalamualaikum warahmatullahi wabarakatuh. So first of all, I would like to give thanks for our distinguished speaker this afternoon as a follow-up session of our accreditation visitation of RAC for bachelor program today. Joining with us, our undergraduate student and our postgraduate student. So from our special speaker this afternoon, we hope you will get knowledge, experience, and of course wisdom from the speaker. Yeah, you will see how good the scientific data brought from the organic chemistry world and also from electrochemistry applied for environmental in situ study. So please give an attention. We will open a discussion from you all. Wish you all a fruitful seminar. Thank you very much.
Thank you, Dr. Asep, for the opening remarks. So without any further ado, I will invite our first moderator, which is our lecturer from Organic Chemistry, Dr. Hari Cahyana. Please come forward to be our moderator for our first sessions.
Thank you. At the Department Chemistry, Bapak Dr. Asep Saimumilah and our lecturer student for the first session. I'm now a moderator for this section 1, synthesis of selected heterocyclic compounds, fluorescence characteristic and bioactivity study. I want to introduce our group research, especially in organic chemistry, and our student also participate here. Our activity work is also in heterocyclic synthesis using Indonesian indigenous natural product, especially low molecular molecule like cinnamon, cinnamic acid, cinnamic aldehyde, and other monoterpene limonene with terminal alkene for more complicated heterocyclic cycle. And now I want to introduce Professor Zanariah binti Abdullah. Time is up for 30 minutes. Yeah. Please. Yeah.
What info? Okay, thank you. Selamat sore Indonesian. Selamat petang dari Malaysia. Okay, right. I try to be as quickly as possible. I think I don't need the 30 minutes, hopefully. So the title of my presentation today is the synthesis of selected heterocyclic compounds, fluorescence characteristic and bioactivity studies. And this is like the development of organic heterocyclic synthesis in the Department of Chemistry. So we are not involved in natural products. We are concentrating on the synthesis. Right? It was okay just now? Is it on? Already on. Let's see once again. Okay, basically the presentation will involve a few things. A basic introduction, what is fluorescence, if you are not familiar with fluorescence. And then fundamental research on fluorescent heterocycles. This particular fundamental research was done for as a FYP, fourth year project student. And then such in synthesis of benzylic imidazole, triazole, oxadazo, etc. This is a PhD work of my students, and I will share with you the current research that we are doing. So I think all of you know what are hydrocyclic compounds. Anybody doesn't know what is hydrocyclic compounds? Is it not in your syllabus? And then you look at the industrial study. Basically, hydrocyclic compounds are, if you remember benzene, so we replace, the simplest system is when you replace one carbon with one nitrogen in the ring. Then it becomes from normal organic compounds into hydrocyclic compound. As simple as that. You can have oxygen, you can have nitrogen, sulfur, and so forth. Okay, that is hydrocyclic compound. So what is fluorescence? Simple term fluorescence is something that glow. It gives light, cahaya. When you put it under sunlight, you can see that it's glow. Or if you put it under UV, you can see some colors. That is a simple term for fluorescence. But in terms of theory, so also simple, I think you know all these things. Basically, fluorescence occurs in molecules as a result of a series of physical phenomena. Normally, it begins with absorption of light. When the material absorbs light, it's either past the matter with no absorption occur, or it can absorb entirely or part of it, and the energy is transferred to the molecule. That is called absorption process. And you know what is the relationship is. And then when the energy absorbed is sufficient, is enough, then the molecule is excited by absorption of proton to produce a transition state known as excitation. At the excitation stage, there are three possibilities that happen. The molecule may return to the ground state by emission of proton. That is fluorescence. That is in terms of theory. What you can see in the eyes, the compound glow. And then all generation of heat, that means the internal conversion, or may change into an excited triplet state from singlet state to triplet state, and then fall back into the ground state, and that term is called fluorescence. Again, fluorescence also makes the compound glow. So what's the difference between fluorescent and phosphorescent is that fluorescence occurs immediately, whereas phosphorescence may take some time to occur. Okay, that is the thing. Right, so I just share some of the work of my undergraduate students. So basically, we started our research back when I came back from UK, long time ago. And first, we are looking at the compound with one nitrogen. And then we moved to 2 nitrogen at 1,3 position. And then we moved to 2 nitrogen at para position. And at this time of the research, we are looking at the possibility of any of these reaction can be used as a sensor, as a compound to detect amine in the water or in whatever liquid. That is the main objective of the research that particular time. And at the same time, since it's very difficult to get chemicals at that particular time in the year of 2000 or before 2000, so I have to sort of like buy, like this one, we have to buy from the chemical company and do the reactions. Whereas for the fluoropyridine, this one we synthesized it when I was in UK. So it's very difficult to produce fluorinated compound for organic chemists, yeah, because it's very reactive and it's dangerous as well. In order for us to prepare the fluorinated compound, we started with aminopyrimidine, undergoes diazotization. Chemistry of amine, are you familiar with that, students? Chemistry of amine, like aniline, undergo diazotization, and then to prepare azodide. No? Yes? It's all basic organic chemistry, but we sort of like make it into research, right? So once we get the azotization and then diazonium salts, and then we react with hydrofluoric acid, we cannot buy this in Malaysia. Okay, cannot buy at all. It's been, it's not allowed for us to buy hydrofluoric acid. All right, so this is some work what I did in the UK. And then we react with amine, various amine to get the amino derivatives. And then we study the fluorescent characteristic. So in order for me to continue working with the pyrimidine derivative, we have to change from fluoro derivative into chloro derivatives. And then after that, we move to the second compound whereby the position of nitrogen is para to each other with chloro derivative, bought it in from the company and do the reaction. So if you're interested, these are the papers that we managed to publish in the local paper at that time. I was still young that time. So we managed to publish like 6 papers for this particular system. Right, so this is example of the, some of the readings. And then it so happened that at that particular time, there was one student, which is an inorganic chemist who would like to prepare some complexes. So he asked some of our compounds here, and then he complexed it with copper. Actually, not only copper, but many other metals, but I just show example copper here. So he managed to synthesize a series of complexes, and this has been published in our Malaysian Journal of Science as well as International Journal of Chemistry. And again, these are some of the results. I will summarize later on. Oh, it doesn't come out. Okay, so from the single system, what we can come up is that fluorescence intensity of derivatives is very weak, and the quantum yield is very low. It's about less than 0.05. And the presence of copper, in case of the complex that we synthesized earlier, it reduces fluorescence intensity further. And the introduction of second nitrogen atoms also reduces the fluorescence further. So if you recall the factors that determine fluorescence is due to the pi to pi star transition. When you have the nitrogen, it's n to pi star transition. So it reduces the fluorescence intensity. The position of nitrogen, for example, in pyrazine, 1,4 position, which is para to each other, and 1,3 position did not give any significant change. And then the substituent electron donating group tends to increase the fluorescence, and electron withdrawing group tends to reduce the fluorescence. That is the early work done by my undergraduate students. And then we move on to fused ring systems. No, it becomes a bit complicated. Start with easy first, then we go to bit complicated. And this one again, we synthesize it in our lab. Again, we're using hydrogen borohydride to form the purine. So you have a uracil. Okay, when you convert double ketone into chlorine, okay, maybe you can remember your functional group chemistry. And then we change the chlorine into NH2, and NO2 is maintained as it is. Reduce the nitro group becomes NH2 at 1, 2, 3, 4, 4th and 5th position, followed by cyclization to form the 5-member ring. And then you play around with the substituent. Either you want F, you want C, or whatever you want your reagent. And we, again, the derivative is still the same. We are still concentrating on reaction of our compound with amines and some amino acid. Again, and then from there we move on to another system. This one is with introduction of sulfur. Just now we have four nitrogen. Now we introduce the sulfur. Again, this is done in the lab. The first part is the chlorination, POCl3 or POCl5. And then you change the the 1-OCl group into NH2, followed by Raney nickel, followed by cyclization with cyanous chloride to form this 5-member ring. This is a 1,2,5-diazolo 3,4-D pyrimidine. And again, the same reaction that we carried out. And that is the fluorescence data. And then we move on to thiazolo and thiadiazolo. Again, looking at the same heterocycles with chlorine, with nitrogen and one N or 2 nitrogen. This one is 2 nitrogen on the 5-member ring and 2 nitrogen on the 6-member ring plus 1S. The synthesis is quite simple, but it takes time. Again, we did the fluorescence studies, and what we conclude from the fused ring system is that for that is for purines, thiazolo, and thiadiazolo pyrimidines. So it's increased number of nitrogen in the ring reduces fluorescence intensity. Introduction of sulfur atoms in the ring also reduces the fluorescence intensity. Similar observation with the presence of electron donating or electron withdrawing group. So that is, we wrap up this research and we move on to synthesis of benzodiazolo and thiazole derivative, plus we did some bioactivity studies. In this case, I only present here a few, but we did quite a lot of biological studies. So first we synthesize bis-benzyimidazole sulfoamides and bis-imidazole sulfoamides. So the starting material is dihydroxyamine, just named general. And then we introduce the living group, the sulfur, this one, so that we can undergo reactions to form either benzyimidazole or imidazole sulfamide. So we managed to produce a few of these compounds where X is either X2A and to 4A, X3, and then so on and so forth. And this particular synthesis has been published in the molecules. And then we also move into to synthesize excuse me, benzyimidazole. We're starting with sorry, diamino. I have to get some water. Diaminobenzene cyclized to form the 5-member ring. And then further react with this compound to form a 2-member ring with a sulfur bridge here. And then we change the NH of the compound 8 to the good and living group. And we study the bioactivity. What we do is we do vitro active bacteria bioassay with 8 compounds and shown just now, and were evaluated by microprobe dilution assays using representative standard grains of gram-positive and gram-negative bacteria, and then minimum inventory concentrations in milligram per mil of the compounds. Again, the test microorganisms were determined. And this part of the research is done by the medical counterparts. It's not done in chemistry department. It's done by somebody else, our collaborator. Or it's too small to sleep. So summary of the results, majority of the compounds studied possess significant antibacterial activity towards selected microorganism. The highest activity observed by compound 9. So which one is compound 9? Down there, compound 9. Okay. And compound in the structure activity, the fourth one, in the structure activity relationship SAR study, it has been reported that incorporation of 2 different pharmacopores in the single crystal enhance the resulting compounds biological activities. And the presence of substituent on the aromatic ring also affects the active bacterial activities, which is, for example, one compound with electron withdrawing substituent, that is nitro in this case, showed a greater antibacterial activity than those with electron donating substituents. And the presence of sulfur atom has a sulfide bridge, you saw sulfide bridge just now, provides a greater stability to the three-dimensional structure of the molecule. And finally, the presence of sulfur in compound 9 has significant contribution to the antibacterial activities, again, gram positive and gram negative. And it is believed to be due to the presence of N double bond CS group. So the next system that we synthesize is the thiadiazolose derivatives, as shown here. We started with thiobenzoic acid, and then we convert the OH to ester plus introduction of CH3, CH2, CH3 at the CH bond. And then we change the OCH3 group into NH2 group. And this is the intermediate compound for further synthesis, which whatever you want to do, as far as this compound is concerned. So in our work, we concentrate on these two compounds only. So what we did was, and then we studied the biological activities. Again, this particular compound, we look at the antioxidant activity using vitro antioxidant and ferric reducing antioxidant. And evaluation is in the vitro cytotoxic activity of selected synthesized compounds, again, human cancer line using MTS assay. Again, this is done in the Faculty of Medicine, not in chemistry. So this is some of the studies. So the summary, parent compound did not show any antitoxic potency against tested cell lines, but with introduction of phenolic group, it shows some cytotoxic potency. And as we all know, phenolic OH is also known as the suppressing reactive oxygen species, ROS. And then try to do it quickly. Current research, now we are looking at the fluorescence sensor, a simple fluorescence sensor that is we're using coumarin react with benzaldehyde to form the fluorescence sensor. And we tested it. This is a fluorescence spectrum of the compounds of the sensor. This is the fluorescence spectra when it react with metal ions. And we believe that our compound, which is this one, the sensor, made from coumarin just now, react with Fe3+, it forms a sum of a complex here, then it reduces the fluorescence. Sometimes you cannot see any color at all. So we can say that the Fs is the fluorescence spectrum of our compound is on, meaning there is fluorescent, there's their colors. The minute we put in iron 3, no more colors. So it's interesting, and still work is still going on, and we currently doing the determination of Fe3+ in water sample, but this is very preliminary results. You cannot say much about this one. So what my student was trying to investigate, the applicability of our sensor in the environment sample. So she studied the recovery studies carried out in the mineral drinking water as well as tap water by water sample doped with Fe3+, and then using fluorescent emission spectroscopy. And the testing of the water sample was performed without any sample pre-treatment at all, just very rough samples. And this is all the preliminary result. You cannot say much about this result, just to share with you that it can be done, but further work is now going on in our lab. Okay, because some of the recovery is more than 100, so I'm questioning her. So she's repeating the work now. And if you're interested, you can go through, you can have a look at this papers, three papers here that published 2020 and 2021. This work is done with a collaborator from Liverpool University. And another research still currently going on with my PhD student is a synthesis of carbon dots, very popular now. What is carbon dots? A member of carbon with organic nanomaterial, in which the sizes is usually smaller than 10 nanometer. So those are the properties of carbon dots. So normally when we prepare the carbon dots, these are the characterization that we do is EDX, FTIR, Raman, NMR, HRD, and spectroscopy. Atom, HRTM, optical study, solid state, UVVs, and fluorescence emission. So my student managed to produce 7 carbon dot. It's a bit simple here. So we have 7 with different colors. You can see here. But again, he is in the 2nd year, so still a lot to do. But very simple synthesis. He started with acetylquinol, and then with acetonitrile, concentrated nitric acid. Sorry, concentrated sulfuric acid, and then he got the protonated resocrinol. And then further react, this one react with each other to form various carbon dots with various colors. He managed to produce 7, and the difference in colors due to the different quantity of sulfuric acid use. Again, as I mentioned, it's still going on. Some of the HRTM analysis, okay, out of 7 CDs that he managed to prepare, only CDs 4 or study under HRTM, it displays a lattice spacing of 0.23 and 0.32. And then he also did some EDX study, and he found out that nitrogen was detected by EDX, which believe that acetonitrile was involved in the reaction. And the percentage of carbon, nitrogen, oxygens of all 7 CDs showed all these small differences. You can see from the table. And percentage of sulfur was also observed. He also do FTIR to see the functional group present. And he also did some Raman spectroscopy, HY-NMR, SRD, optical properties of CQD, etc. Again, as I mentioned, this is early work. He's struggling now. And his work has been published in Applied Physics A. If you're interested of the method and etc., you can go through and look at this paper. And he just finished writing a second paper is the application of his carbon dots. But still, we're still waiting for the comment from the assessor. And finally, I would like to express my gratitude and thank you to Ministry of Education and Ministry of Higher Education of Malaysia for giving the grant, Universiti Malaya, and all my research students and collaborators. And thank you to all of you for listening. Thank you.
Yeah, we have still 7 minutes, and I want to take a question for students. Please raise your hand if you want to discuss a question. Yeah. Okay, your work in your laboratory, for example, Salma, Nadia, and student, you study heterocyclic in your laboratory. Okay, please raise your hand. Yeah.
Thank you for untuk waktunya. My name is Salma Fitranisha from Research Organic Chemistry, and I recently I researched about oxadiazole and thiadiazole, and I want to ask about what is different. Maaf, pakai bahasa Indonesia boleh Pak? Boleh. Oke. Saya kan penelitian tentang oxadiazole dan thiadiazole. Terus kan apakah kan Ibu juga meneliti tentang aktivitas senyawa tersebut ya Bu ya? Oh Ibu maksudnya oxadiazole dan triazole gitu. Apakah ada perbedaan dari senyawa aktivitas antara O dan N gitu? Bu boleh nanya yang kedua Bu? Oh boleh. Iya.
So you're working on with oxygen. I'm working on with nitrogen and sulfur. That's what, all right. So again, they have different reactivity. You cannot compare like that. You cannot compare each other. You cannot compare me with Pak Asik, for example. So it depends on the compound itself, and also the position of the substituent. Substituent, kumpulan penukar ganti. I don't know what to call it in bahasa Indonesia. Substituents.
And join from functional to carboxylic and join more cyclic derivative using nitrogen and oxygen. You reaction between fatty acid and thiocyanocarbacid and cyclic contain oxygen and nitrogen. But same in fatty acid, long chain carbon. How about the different biological effect?
Oh, biology, you cannot tell the theory. Yeah. Normally, I have to do the experiment.
The structure maybe have fluorescence.
Fluorescent properties, it depends on the, okay, you have oxygen, you have a fatty acid, very long fatty acid. So normally the long chain, it will reduce the fluorescence because it's moving like that. When it absorbs energy, energy will lost when the long chain moves. And another reason is the fusion of oxygen also reduces the fluorescent intensity. But the fluorescent, they don't like nitrogen, oxygen, sulfur. They don't like. They like hydrogen. Okay. Okay, you're welcome.
Yeah. Thank you. Maybe satu lagi. This one in this room, okay? One more. Yeah. Oh, you have second question? Yeah.
But is out of context, Bu. Boleh kan, Bu? Boleh. Kan kalau penelitian saya ini kan untuk ini mereaksikan asam lemak ditambah tiosemikabajida dan semikabajida menghasilkan tiadiazol dan oksadiazol. Dan saya ini saya using catalyst nanoparticle like CuCO3, and then I want to apakah can be separated only paper chromatography, or must be separated by centrifuge. But kalau sederhananya, apakah bisa nanopartikel itu bisa didiamkan saja gitu, Bu, untuk pemisahannya? Terus saya hanya pipet seperti itu. Yes. Yes. Katalis. Iya. But apakah ada cara lain? Another way? Ya. Selain. Iya. Solid. Iya. Iya. Oh. Can ya. Iya. Oke, Bu. Makasih, Bu.
Okay, thank you.
Am I still allowed to ask questions? Okay. Okay, so my name is Hasan Maulana Ibrahim, and currently I'm on my last year. It's very interesting about your session. I would like to ask, what I know that fluorescents have a difference of colors, right? Like red, green, yellow, and something like that. And we know that colors came from a difference of wavelength and something like that in spectrums. And in this synthesis, in Prof. Zanariah's research, this difference of colors, of course, also come from different wavelengths. And these different wavelengths, which are they came from? Is it from the difference of materials that are used, or difference of functional groups that are in the heterocyclic compounds, or anything? Because it's very curious for me, where does the difference of wavelength came from the synthesis of selected heterocyclic compounds? Thank you. So it's based on the amount of the compound itself. And so is so is it possible that, for instance, my goal is to synthesize the fluorescence for white colors, not green or maybe not red, and to know the colors is white is that to know that it is, which ones it is white or not, based on the compounds itself or other factors. Yes. Yeah. Okay. 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 Thank you so much for your time.
Waktunya masih. Udah cukup. Oh ya. Okay, because of the limited of time, I want to express thanks for Professor Zanariah with session topic very interesting, synthesis of heterocyclic. Please give applause for Professor Zanariah. I want to.
Thank you so much, Prof. Zanariah, for delivering such a very interesting topics, and also to Dr. Harry for moderating our first sessions. So we will continue to our second session, which is a lecture from Professor Katherine Holt from University College London, which will be delivering her topics entitled, What is the pH at an electrode surface? The importance of in situ studies in determining the true nature of electrocatalysts during operations. So without any further ado, I will invite Dr. Rahmat Wibowo as our moderator for these sessions. Pak Bowo, you are kindly requested.
Okay, good afternoon, everybody. So I hope you still have energy to listen, yeah, or to learn from Professor Holt today. So she will be talking about the pH of the electrode surface. So Anyone of you who are from the electroanalytical chemistry class may learn from this lecture. Okay, so without any further ado, please, Professor Holt.
Thank you. So I hope you have energy to listen. I hope I have energy to give the talk. It's been a very long day. So thank you for giving me the chance to talk about this research. I've put here the paper, which kind of describes kind of a lot of the content of this talk, and listed the people who are involved in the research. So let me go back to, first of all, kind of another earlier paper that we published to try and give a bit of background and context and justification of why we were doing this research. So we were looking at conversion of carbon dioxide, CO2. So as you all know, it's very important that we try and find ways of reducing the amount of CO2 that we produce, and also being able to capture and perhaps use the CO2 that's excess in our environment. And one of the ways to do this is using electrochemistry and to reduce CO2 to form molecules that we might want to use. So molecules that can be a fuel, or molecules that we could use as feedstocks for other reactions. And to do this, you either need to use a lot of energy, which produces a lot of CO2, so that's a problem, or you need to develop a catalyst which will carry out this reaction at a lower energy. So the idea of this work is to try and find a catalyst which will be able to reduce carbon dioxide to produce some kind of useful chemical. So we were looking at iron sulfide materials, so iron sulfide, as I've said here. So why did we decide to look at iron sulfides? You have to have a reason. You can't just pick any old chemical. And part of the motivation for this came from a completely different field of research. And this field of research is about the origins of life. So there's a lot of research in chemistry that goes to try and understand how life could have evolved on Earth, and thinking about the first step, which is how do you make small organic molecules? Where did they first come from? And one of the theories is that the first small organic molecules came from the reduction of carbon dioxide on the surface of minerals that were available in early Earth. And those minerals that they believe were present were found under the ocean in these kind of black smoker type situations where iron sulfide and similar minerals were made. And these are very reactive, and that dissolved carbon dioxide then underwent a reduction reaction to make small organic molecules. And that was how life came on Earth. So the reason why people think this might be the case is that if you look at the enzymes in nature, so some in our bodies, you can often find iron sulfur kind of little clusters in those enzymes. So the idea is that we evolved to have these because these reactions took place on iron sulfur minerals to start with. So that's what the theory is. And if you look at these clusters, so this is a representation of an enzyme, and the active site in an enzyme, one of these iron sulfur clusters, it has a very similar structure to the structure of metal sulfides, like one called greigite, which is one we're going to be studying. And so what we did is we made this iron sulfur material, we put it onto an electrode, we applied a negative electrode potential to carry out reduction in the presence of carbon dioxide in different pH solutions, and that we found, and then over time we measured how much product was made, and the product that was made was mainly formic acid. So you could reduce carbon dioxide to make formic acid on the surface. So there's an important thing to note here, that we did this reaction over a very, very long period of time, and the amount of formic acid we made was very, very small. So these materials are catalysts, but they're very bad catalysts, okay? So we haven't made a fortune. There is no business that we've set up to use this catalyst to make formic acid. because it's a very bad catalyst, but it is quite a good sign that it could be important for the origins of life mechanism rather than as a catalyst. So coming from this, there was the question of why it's such a bad catalyst, and also how we can model catalysis. And initially, when we had some collaborators who did some computational work, they modeled this on an iron sulfur surface that was completely stable and unchanged. And I thought, I don't think that's going to be true. I thought that during the reaction itself, it was very likely the catalyst might react or would not be stable. So that is the point of this research. So this is the material that we've been using. It's called greigite. It's Fe3S4. So it's a mixture of iron 3 and iron 2 oxidation states. This is a high resolution TEM image. And it shows that they are kind of nanoplatelets. They're very, very small platelets. And we synthesized them within a solution containing olailamines. This is an amine with a long hydrocarbon chain. And this also acted as a capping agent. So it protects the surface from oxidation. So why is it important that we protect the surface from oxidation? So here I have, wrong way. Here I have what is called a Pourbaix diagram, or it's sometimes called a pH potential diagram. So what I have on this axis here, my x-axis is pH. So I'm interested in the range 6 to 14. And on this axis, I have my electrochemical potential. So I'm interested in the range 0 going down to minus 0.6. And as you can see from the lines on this diagram, this gives us the regions where different species are stable. So it tells you what species are present at different pH and at different potentials. And the important thing here is that greigite is actually only stable in this tiny region here. So this diagram is telling me that really, if I go to a higher pH, greigite should change into green rust. So this is an iron oxide material. And if I go down to lower potentials, if I reduce it, it should change to FeS and then eventually to metallic iron. So the capping agent, we're hoping, will keep it stable a bit longer so it doesn't immediately just turn into rust, into oxide. And then what we're going to do is we're going to put it onto the surface of an electrode, and we're going to see what happens when we apply a reduction potential to the surface. So in this figure here, I'm showing what's called a cyclic voltammogram. So I don't know, some of you might know cyclic voltammetry, some of you might not. Don't worry too much about it, but basically what this shows is on this axis here is the potential that I'm applying. So what I'm going to do is I'm going to reduce the material. So I'm going to start at 0.2 and move down to minus 0.8. So when I go in this direction, I'm carrying out an electrochemical reduction. So the electrode will be gaining electrons. And as I do it, I measure the current. And if a current flows, so if the value is not 0, if a current flows, it's telling me the reaction is taking place, okay? And if the current is a negative value, it tells me it's a reduction current. So what I want you to do is just look at the black line in this diagram. So ignore all of the red lines, just the black one. I'm going to start here. I'm going along in this direction. And as you can see, the line is flat. Nothing is happening. So no reaction is taking place. Then at point R1, I start to see a negative current flowing down here. And that tells me that there is a reduction reaction taking place. So I'm reducing the greigite or something on my electrode surface. So I'm doing this reaction at pH 6.8, and there's no CO2 solution, no CO2 in the solution at present. So really what I'm doing when I'm going from 0.2 down to minus 0.8 is the equivalent on this diagram here of starting at a positive potential and moving to a more negative potential down this green line. So the green line is drawn at pH 6.8, and I'm starting from the top and I'm moving down. So what I would expect to happen is that my greigite hopefully will be stable because I put the layer on it. Then I will get a reduction of the greigite, my Fe3S4 to FeS, which is just iron 2. And then I should get another reduction to iron 0. So that's what I'm expecting to happen. So what does that mean is happening on my cyclic voltammogram? So as I said, I start to get a reduction reaction happening from R1 here, down here. So that's at about minus 0.5 volts. I start to get this reaction. So one thing it could be is it's the reaction of my greigite going to FeS. So it's the iron 3 going to iron 2 here. The diagram predicts it should happen at about minus 0.2. But it might be that the kinetics are very slow. So it means that maybe I need to go to minus 0.5 to get the reaction to happen. So it could be that my reaction is this one. The greigite going to FeS. So just a change in the oxidation state. However, the other thing it could be isn't on this diagram at all. It could be the fact that I'm in water and a reaction that can take place is the reduction of water. So the 2-electron reduction of water gives hydrogen and 2 hydroxide. So that reaction could be the one that's taking place. So how do we work out which it is? So the first technique that we looked at was using something called in situ X-ray absorption spectroscopy. So to do this, you have to visit a synchrotron facility. You can't do this just generally in a lab. It's an absorption method. So basically you shine X-rays onto your sample and you see what energies have been absorbed. And that will tell you about what species are present in your material. So what I have is this is a cross-section through the side of my electrochemical cell. I have my working electrode, so my main electrode that I'm applying the potential to, and I've put my sample right on the surface of the electrode here. So that's where my greigite is. Then my X-ray kind of comes in here through a window onto my sample, and I measure the X-ray that kind of comes out. So it will tell me what's been absorbed. And then I have my 2 other electrodes in the solution, and I have my electrolytes in the solution as well. And what are we measuring? We're measuring what's called the iron K edge. So basically, we're measuring absorption of the iron species only in the sample. And this will give us information on the iron oxidation state. So whether it's iron 3, iron 2, iron 0. It will also give us information about what it's bonded to and how it's bonded. So it will tell you if it's bonded to sulfur, to oxygen, and what kind of arrangements of the sulfur or oxygen around it. And we're going to do the reaction in exactly the same conditions as I showed on the previous slide, at pH 6.8 electrolyte, but with no CO2. And we're going to compare what happens if we don't have a potential and if we do have a potential. So this is the kind of data that we get. The technique itself is called ZANES, or X-ray absorption near edge structure. But the important thing that you have to notice is if you just look at the spectrum that is shown in black and the one that's shown in red, they both look exactly the same, basically. They're on top of each other. So to interpret these spectra, we just need to look at some of the features in the spectra. So the important features to look at here are the feature that I've labeled B, which is this shoulder to the spectrum. And then these features up here, which are the higher intensity, which are labeled C. So C is what's called the white line intensity. And this is the first allowed transition for iron. So it basically tells you that it's iron and what oxidation state it's in, its position. B is a kind of very special feature that we only see for iron sulfide materials, because it's a transition that's not allowed usually for iron, but the bonding with sulfur, because sulfur is very soft, means that you get some mixing of orbitals, which means you get some transitions which aren't usually allowed, which are allowed. So basically looking at the spectrum, what we do is we compare the spectrum to known models, to known compounds. And by doing this, we are able to say that this is 100% greigite. So the red spectrum, the black spectrum is the dry greigite, and it matches greigite. So it is greigite. And the red spectrum is a greigite that's been left in the solution at pH 6.8 for 1 hour, and it's still greigite. So it's showing that it's stable in the solution. And both of them are showing that this is an iron sulfur material. So ignore the blue spectrum for now. I will come back to that a little bit later and explain it. So what we did then is we applied some potentials. So first of all, the one in black here is when we applied a potential at which no reaction takes place. And the spectrum is the same as for the dry greigite, so it's unchanged. Then we apply a potential of minus 0.6 volts. So that's where that reaction was taking place, where we know the reduction happens. And what you can see is two things. First of all, this shoulder disappears, so it's no longer there. And then secondly, the intensity in this region goes up, so you get an increase in that. And both of those features together tell us that FeS bonding is converting to FeO bonding, so it's turning into an oxide. What we don't see happening is that iron 3 is being reduced to iron 2 or iron 0, because if that was the case, this spectrum would all shift, it would all move position, and it doesn't, it's in the same place. So only the shape changes. And if we fit this to model compounds, this tells us that the material we end up with is 60% greigite, so the original, and 40% some type of iron hydroxide species. So this confused me a lot. We did these experiments, and it took, I think, about 3 years before we managed to understand them enough to be able to publish in a paper. Because to an electrochemist, if you apply a reduction potential, you don't expect something to turn into an oxide, because that seems like it's being oxidized, right? Very, very confusing. Took us ages to work out what was happening. Especially when you look at this diagram, which suggests something else should happen. And that reaction that we initially thought would happen would be iron 3 went to iron 2 and then maybe iron 0. But we see no evidence for that reaction happening. What we do think is happening potentially is that the current is due to this reaction instead. So the reduction of water going to hydrogen, and importantly, this reaction produces hydroxide right at the surface of the electrode. Now we are using a buffer solution, which should be able to buffer the pH. But if we're producing a lot of hydroxide, it might not be able to buffer it quickly enough. And if that happens, the pH would move from 6.8, where it starts, all of the way into this region here. And all of a sudden, we're in the region where the rust, the hydroxide, the oxides, and this species fuggerite, which is oxide or hydroxide species, are stable. So our question was, were we getting an increase in the surface pH, which was causing some kind of transformation to oxides or hydroxides? So the way that we investigated this was another in situ technique. This is in situ infrared spectroscopy. So I don't know, you probably, most of you have learned something about infrared spectroscopy, but the type that we used is something called attenuated total reflectance infrared spectroscopy, or ATR-IR. And how this works is that we have here a prism, and the infrared beam comes into the prism. It undergoes total internal reflection at the surface of the prism and then comes out again. But some of the waves, so some of the energy can penetrate a little bit above the prism. And if there's a sample there, it will absorb the infrared spectroscopy, and you're able to measure the vibrational or infrared spectrum of whatever is just above the prism. So that's how the technique works. So what we do is we put our sample on an electrode again, so it's just here, and we push it very close to the surface of the prism, and then we clamp an electrochemical cell on top, and then we will hopefully measure the infrared spectrum of whatever is just above the prism. And this here is a kind of bigger picture of that region. So you can see here the infrared is coming in, it's reflecting on the surface and coming out. And we have this bit of wave here, which is called the evanescent wave, which penetrates just above the surface of the prism. And it's able to measure a spectrum of whatever particles are there, and also the solution species that it's dissolved in, because it's in an electrolyte. And it's on the surface of an electrode, so we can apply a potential as this happens. So the type of spectra we record are called difference spectra. And they're different spectra because we're measuring changes in absorbance as a function of the wave number. So what we do is we take a spectrum under conditions where no potential is applied. Then we will take another spectrum where the potential is applied, and we will, what we're showing here is the difference between the two. So it's changes from no potential to potential being applied. So the top example, you can see we've applied a potential of minus 0.05 volts. This is where no reaction was taking place. And you can see it's relatively flat. There's a few small changes, but they're very small. And this means that there's no change in the species in that region. So there's been no reaction. Then we apply the potential at which we know the reaction takes place. And you can see that we get changes in the spectrum. And the important thing about the different spectra is if the peaks go up, it means you have more of that species, or the absorption for those species has gone up. And if it goes down, it means that you have less of the species, and the absorption has gone down. And we're doing this solution in buffer solutions, as I said, 6.8. And these are made up of phosphate species. And the great thing about phosphate species is that they are very infrared active. And all of the different phosphate species have a different spectrum. So you're able to identify which ones are present and kind of how much. So the important thing really is if you look at the spectrum that's in red, so this is at early times, we get a big peak that goes up that's due to phosphate. And also we get an increase due to HPO4 2-, and we get a decrease that's due to H2PO4-. So we've got more phosphate, more HPO4 2-, and less H2PO4- during this process. So what's happening? So let's remind ourselves about the different phosphate species that are present in phosphate buffer solutions. So if we start with the most acidic solution, up here, we have phosphoric acid, H3PO4, and this can lose a proton to give H2PO4-, and the pKa for that process is 2.16. So that's under acidic conditions. Then the H2PO4- can also lose a proton to give HPO4 2-, and this has a pKa of 7.21. So this is kind of the composition that we use to make up our pH 6.8 solution. It's a solution that contains about equal amounts of the H2PO4- and the HPO4 2-. Then if we go to more alkaline conditions, what we can see is the HPO4 2- can lose another proton to give this phosphate species, PO4 3-, and the pKa of that is 12.32. So this diagram here is just a different way of showing these. So it's telling us which acid species are present in the solution at different pHs. So here I have pH, and this is the relative amounts of the different species. So in the acidic solution, I start with lots of H3PO4, but as I go to more less acidic solutions, this goes down and the H2PO4- goes up. And then this starts to go down and the HPO4 2- goes up. And then finally, under the most alkaline conditions, I get an increase in PO4 3- and a decrease in the HPO4 2-. So what's happening is we think that the spectrum is showing that when I apply the potential, I now have a signal in the infrared for PO4 3- that wasn't there before, and it wasn't there in the starting solution. So the starting solution only had these species. So if I have PO4 3- in my solution, it means I'm in this region here, which tells me that the pH near the electrode has to be greater than 10 at this situation. And as I showed before from this diagram, at pH greater than 10, I can turn my greigite into iron hydroxide. So that's what we think is happening. And to kind of prove this a little bit, I'm going back to this spectrum. And before I told you to ignore the blue one, but you can look at the blue one now. And the blue one is basically what happens if you take the greigite and you just put it for 1 hour in a solution of pH around about 11. And you can see that I've lost the shoulder and I've increased the intensity, which shows that I make the hydroxides under those conditions. And you can see the spectrum in blue here more or less matches the spectrum that I get if I apply the potential for that time. So it seems to suggest that that's what the pH is. What we also did was we took some of the sample after we'd done these experiments, so after we'd applied the potentials, and we looked at them with high resolution TEM. And what you can see is we have a kind of core shell type structure. So we have the core of the material, still looks like greigite. So it's difficult to see, but there are kind of lines in here that you can see, which are the lattice of the greigite. So it shows the greigite is still there in the middle. But then on the outside, we have maybe about 10 nanometer thickness, lighter region, which is all very amorphous. It's not crystalline, which we think is the hydroxide on the surface. So the greigite stays in the middle. It's not changed, but the hydroxide is on the outside. The interesting thing is that if you take that sample and you carry out XRD on the sample, so X-ray diffraction, so this is a very common technique for doing characterization of materials to see what's there, all you see is the spectrum for the greigite. So it looks as if it's the same as the starting material. And that's because XRD can only see crystalline samples. Okay, so it can only see the crystals in the sample if it's ordered. So if it's a sample which has kind of crystalline structure in the middle, but on the surface has an amorphous layer, this means that it won't see the amorphous layer. So it can't see that you've got that hydroxide. So it looks as if it's the original material. So to come to my conclusions, I hope that I've shown you that you can see quite dramatic pH changes at the electrode surface because of redox reactions, if they produce hydroxide or if they produce protons. If this happens, then your electrode material can become unstable if you don't choose a material that is stable at different pHs, and it might change its composition. And things like XRD that you might use to study the stability of a catalyst won't see this. They can't see this change. So you need to design other in situ methods to be able to look at this. And the in situ infrared spectroscopy is quite a good technique using these phosphate species to tell you what the pH changes are. And finally, I've given the reference to the paper. And thank you for listening, and I'm happy to take any questions.
Okay, thank you, Professor Holt, for this interesting lecture. So if there is any question from the students or audiences, yes, thank you.
Thank you, Prof. Okay, hello, Prof. Katherine Holt. Thank you for the opportunity. Allow me to ask you about the question regarding your very interesting topic regarding about catalyst. In here, I want to ask you about how does performance of the capping agent affect the structure of the nanoparticles, and what things can influence and what is the mechanism of nanoparticles to convert a compound into a new compound? Thank you.
So the capping agent question, yeah, it depends on the capping agent. And one of the reasons we picked this one is that because it's an amine, and because amines have been used to capture carbon dioxide, so they're a well-known carbon dioxide capture, we thought, we didn't know if it would help, but we thought that it might be an additional good reason for using this. A problem with capping agents is, of course, they can block access of the reactants to the surface. So that's something. So you need to pick a capping agent that will help with stability, but won't stop the reactant from reaching the surface. So we believe that it does passivate the surface, so it does stop it reacting. But if you cycle it enough, then eventually it will maybe come off. I don't know. We didn't. Sometimes in the infrared spectroscopy, we think we can see it, but it's not always there. So yeah, it's a good question about what actually happens to it, whether it stays or by the time you use it as a catalyst, it also goes as well. And then what was your second part of your question again? Oh, okay. So what's the actual CO2 reduction mechanism on the surface? Yeah, very good question. So I think there are many, many papers on the reduction of carbon dioxide with many different mechanisms. All of them require carbon dioxide to absorb onto the surface in a way that will activate it. So the problem with carbon dioxide is that it's not very reactive. And a way to make it more reactive might be as if it absorbs onto a surface and some electron density perhaps goes from the surface into the bonds of carbon dioxide and weakens the bonds, then it will become more reactive. It's kind of known that it can go onto the surface, and you know, carbon dioxide is usually linear. It's well known it's a linear molecule. What you want is it probably to absorb on the surface, maybe with the carbon and then some electron density to be donated so that the molecule becomes kind of bent and weakened, and then it can react. But there are some mechanisms where it absorbs on one of the oxygens and then also becomes weakened. What you don't want is for it to absorb on the surface and be so stable on the surface that it just forms like a carbonate on the surface, which can happen. So it's that kind of balance between needing it has to absorb on the surface to weaken the bonds, but you don't want it to absorb too strongly, otherwise it just reacts with the surface. So there's not really a universal, there are known mechanisms, but it will depend on the material according to which mechanism it goes by. And carbon dioxide's more complicated because there's one route that goes to formic acid, and then there's another route which makes, first of all, carbon monoxide, CO, and then if they're close together on the surface, they can couple, and then you get carbon-carbon bonds or carbon-carbon-carbon bonds. That usually happens on surfaces or on copper. It's well known happening there. And of course, people are very keen on that reaction because you want to make more complex molecules. Formic acid is okay to make, it's fine. You know, we can use it, but and you can use it in a fuel cell, and there are reasons you'd want to use it. But people want to develop catalysts that will enable carbon-carbon bonds to form, so you get more complicated molecules. Okay.
Okay. Okay. Bu Yuni maybe want to ask question.
And yeah, I have two questions actually. For this X-ray absorption spectroscopy, did you do exaph as well, or just scenes? Yeah, because then maybe we can see the environment of the iron after it changed from sulfur to oxygen. That's my first question. And then the second question is due to in situ IR spectroscopy for the phosphate. I also noticed that when you subtract the the right with previous before and after the reaction, I saw that the peak for carbon dioxide peak, I noticed it's a negative peak. Yeah. So could we observe that, and when we observe that, we can say something about the content of the carbon dioxide that maybe it's decreased or increased during the reaction or something?
Okay, yeah. Two
Okay.
good questions.
Thank
Good
you.
question. So with the XAPS, we had the data. It's difficult to get very good data for this because it's in solution. So the X-ray absorption is quite, the water absorbs, and so we did have that data, and I think the PhD student, she wasn't my student, but I think that it's in her thesis probably, but we never used it in the paper. So we looked at it enough to be able to say it's Greigite, but it was, especially when you have the mixture afterwards, it's difficult to kind of tell what information you would get from them. Yes, exactly. Yeah. So, yeah, I mean, when we did the measurements, we collected all of this, but yeah, there's always the background and all of that. Yeah. So I don't know if the data in that region was ever good enough to really draw any further conclusions, but I'm not an expert in that. So, but I think that she probably had a go at fitting it. Yeah, exactly. Yeah. And it's kind of, I think we're assuming with the XAPS as well that we're sampling the whole sample as well, that it's bulk. I think it's probably fair that we're doing that, but it's still unknown, right? What penetration, etc. As for the infrared, yeah. So with those experiments, we didn't actually have any CO2 in the solution. So I think the change in the CO2 that you see is background. It's kind of, it's due to just somebody stopped breathing or breathed more over the instruments or something like that. But in principle, you probably could use it to see if you had CO2 in solution. The issue actually for us is that we use a diamond prism, and that CO2 band is kind of in the region of the diamond prism, which absorbs very strongly. So we tend not to use data in that region very much if we can help it, because the signal to noise is just so rubbish there that it's difficult to say. Yeah. Thank you.
Okay. Okay, Prof. Bakri.
Hello.
Sorry, it's a bit out of the culture because you're talking about in science, but I would like to talk about in nature. I learned a bit about the land of tidal waters. We got a lot of land. Sometimes they're watery and sometimes going down. Actually, it's quite a lot. What we call it, Fe3S4. We call it. Is it period something?
Oh,
is it similar?
Yeah, a different iron sulfur.
This is Fe2S or something like that. But actually, we got a lot of Fe3S4, and we use land for rice. What's it? Growth. Rice. Right. And sometimes, because the pH is changing, they produce hydroxide things.
Okay.
And it's brown, and we cannot grow rice at that time. So like they put they throw coppers and zinc nitrate, so they just make it down there.
So is it like some kind of Fenton reaction or something like that on the iron that is changing the pH?
Right, but the problem is, and you told here that the pH is 10, but it's only 6 pH. They produce the hydroxide thing. Is it the same procedure?
It could be, yeah. Because I think if you produce a lot of hydroxide locally, like just in one region, and it doesn't get buffered or it doesn't dissipate, you can end up with a very high pH very locally, even though you haven't produced very much hydroxide if it was diluted in a whole larger volume, right? So you get local high pH.
Yeah, because
So-
it's produced also the sulfuric acid, something like
Yeah,
that. So
yeah,
there's the pH down, but it's produced the hydroxide.
Yeah, yeah.
Okay, thank you. Do you still want to have another question?
There is
Okay. Okay. I'm just wondering, why do you choose phosphate buffer solution for these experiments?
Okay, yeah, good question. So to start with, there was no real reason apart from it's a good way of controlling pH at around 7. So it seemed a good place to start. We wanted to keep things as kind of under as neutral conditions as possible. That was the whole idea. If you're copying origins of life, for example, you want to have kind of near nature, neutral pH. So phosphate buffers really well close to 7. Afterwards, we realized it was a really lucky thing that we had this phosphate because it's so brilliant for infrared spectroscopy and seeing what the pH change is. But I would be pretending if I set out to design an experiment to work out how to change the pH of an electrode with phosphate. It just happened to be, we did the spectrum and it was just like, why has that done that? That's crazy. Oh, but it fits in with the other crazy result that we got. So that makes sense. Yeah.
So actually we can use on any buffer solution to study
So
it.
you could change it, and they would usually, they're quite often infrared active. So you could do borates or acetates if you wanted to go more acidic. Yeah.
Okay, thank you. Professor Holt. Okay, Bu Tessa, do you want to ask a question? Okay, so maybe this is the conclusion of our lecture today. And would you please join me to applause Professor Holt? Thank you.
Thank you so much, Pak Bowo, and also Prof. Holt for delivering such a very interesting topics. So before we close our guest lecture today, I will invite Ms. Kim Powell to give us a little bit information about Royal Society Chemistry, about the membership, benefits, and also offers available. So Ms. Kim Powell, you are kindly requested.
You'll be pleased to hear I haven't got any slides. I just want to remind you all, how many students have we got in here? Who's a student? No students? Loads of students. Keep your hand up if you're a member of the Royal Society of Chemistry. Got some members? Good. Those of you who aren't members, because you're on an accredited course, you can get student membership for free. So it's always worth having a look. If you go onto our website and go to the Join Us page, you will need to type in a code at the end, at the pay bit, and the code is Catalyst 100. I will send it to your lecturer so that you'll have it. But it's worth joining us because you'll get a monthly newsletter for students, you'll get access to Chemistry World online, and you'll get other bits and pieces as well. We also help you out with Student Chemistry Society. Do you have a chemical society here? Well, we can give you some ideas for that, maybe help you out with that. And also there's lots of interest groups. So when you're doing your projects, if you've got quite specific interest, there might be a group that you can join that will then maybe help you with your projects and things like that. So well worth joining, and even more worth joining because it's free, but only because you're on an accredited degree. That's all I've got to say.
Thank you so much, Ms. Kim Powell. So students, you are free to join. So please open the websites and we will give you the code later after we received it from Ms. Kim Powell. Okay, before we close our guest lecture today, I will invite Prof. Zanariah and also Prof. Holt and also Ms. Kim Powell. So our department, the head of department chemistry, will give you the token of appreciations for your time and contributions for today. So please come forward. And Dr. Asep Saifumila, as the head of Department of Chemistry, will give the token of appreciations for
Ya. Itu dulu. Aku nanti sama Pak Bakri. Oke, baik.
So for all of the participants, please come forward. We will have group photos.
Okay.
Terus gimana kira-kira?
Okay, so for all of the participants, please come forward. We will have a group photo first with our speakers. So, okay, please come forward.
Di depannya sama di belakangnya tinggi aja ya.
Okay, thank you so much for all of the participants. Okay, so this is the end of our guest lecture for today. So thank you so much for all of the students who is coming to this guest lecture. Hope you will find this lecture very insightful. Thank you so much and good afternoon. Wassalamualaikum warahmatullahi wabarakatuh.
Ini saya akan aja begitu. Pakai ya sudah.